Good afternoon. How are you doing today?
Doing well.
Well, doing well. I would assume that most of you never met me in person before, and this tells you a lot about me. For example, that I can hide well. So we have the plan for today is to learn about multiple different topics, interesting topics from control systems related to design of controllers using Bode diagrams, frequency domain methods. And I assume that you already learned a little bit about root locus and how you design in root locus domain by moving poles, changing gains. But now we have additional things that we need to learn. And your goal is to stay focused because this is kind of tough topic, a little bit difficult. You need to stay very focused on procedures that we are going through. And I will show a few examples just to make sure that you know all the steps that you need to make. This is a little bit of an art because after you design it using these steps, you still need to refine a little bit. You need to move a little bit the poles, a little bit the gains until you get the performance that you want from your system because you will never get it exactly right. I assume that in root locus, you also seen something like that. You need to play a little bit with different things before you get it right, but it gives you a good start. So this is your goal, to stay focused and to pay attention to the topic, okay? My goal is that this lecture is not be too horrible that you will want to go and continue graduate degree in our department, okay? Because you will see me much more than in the graduate degree from that courses, all right? Okay, so why do we need that new methodology using frequency domain methods? Instead of just using root locus, putting poles wherever you want them to be, putting some lead network, LED network, you get it right, all right? But first of all, it's much more computationally simple in a sense. And this is a simple method for system design, but more importantly, these methods are closer to physics, which means that the real meaning of the system is described much better in frequency domain and not in root locus domain, which is pole location, zero location. You cannot directly connect location of poles and zeros to important things like settling time, overshoot. You have only approximations of some kind. And in frequency domain, it's much more physical. So you have some physical meaning behind Bode diagrams. It's actual gain response to particular frequencies. And these frequencies appear in actual physical systems. So it's important to understand what you do with that type of gain systems. And you have a few additional benefits. And one of the benefits is computationally straightforward. So you have just formulas, put a number in the formulas, going by the procedure, and eventually get close enough result. Okay? And you can do that even by hand computations. You don't need MATLAB or something like that. But you can say, like, look, we have MATLAB. Why would we care? So this is not huge advantage, really. Because now with computational tools that we have, saying that you can do that by hand is not a big deal, really. Right? You can do that with MATLAB. It will be fine with root locus as well. No problem, really. So this is not big advantage, but this is much bigger advantage. So typically you need to develop system which requires not a single controller, but cascade controllers, multiple things that you put together to perform well. Okay, so it's not as simple as just putting one pole and one zero or just one gain or something of that kind. Typically, it's much more complicated, and systems are much more sophisticated in reality compared to what we typically do in examples in this course. So the idea is that in frequency domain, after you gain some experience, it's much easier to develop multi-parameter controllers with many different poles and zeros. And you can think like where you put them, how you modify them to satisfy your characteristics and so on. So it gives you flexibility of design that you cannot have with root locus. Root locus cannot handle more than like 2 parameters. So one parameter will be some gain, another parameter will be some other variable like location of pole or something. But other than that, it's difficult. All right. Now, additional thing that with root locus, it's very difficult to use derivatives. It's not working well, okay? And you cannot even implement derivatives in reality because ideal derivative requires future time. So it's not causal system. derivative, okay? And controllers with derivative need to be only approximated. And approximating that in locus domain is extremely complicated. Okay, so people just do not do that. In frequency domain, just the difference between pole and zero is just how you're going up with Bode or you're going down with Bode. Still Bode, same thing, okay? I'm not worrying about that kind of problems at all. If you have zero, it's zero. If you have pole, it's zero. Doesn't matter for you, really. So it works the same way. And you can satisfy multiple requirements like settling time, overshoot, steady state error. But you can also handle bandwidth. So who remembers what bandwidth is? The system. What does that thing? Why should we care? Any ideas about bandwidth of the system using Bode diagrams? Like what is bandwidth of Bode plot? Like you have typically plot which goes flat or down, then it breaks, somehow going 20 dB to decade, 40, whatever number of poles you have, and so on. So what is the bandwidth? So bandwidth is defined as minus 3 dB after the flat part. Like when you get to the down 3 dB, the width from 0 dB, from 0 hertz to that point is bandwidth of the system. Which means if Bode falls down later in frequency, this is broader bandwidth of the system. If it is like low pass, which is cutting here, this is narrow bandwidth of the system. Now, why should we care? What is good about having big bandwidth? It means you are having gains which are pretty high for higher frequencies, right? Low bandwidth means that you're cutting all the high frequencies. High bandwidth means it's broad band. So what is good about it?
The system that you develop is more stable and multiple.
It's not necessarily more stable. It actually can be more unstable. Depends. Yes.
Could more bandwidth mean more noise?
But this is disadvantage of higher bandwidth, yes. So big disadvantage of having wide bandwidth is that you introducing more noise disturbances and they all affect your system. And then obviously it's not good for the system. But what is good about it?
Handle more like individual components?
Not necessarily. No.
You could add more data.
What do you mean by more data?
Wider bandwidth. Longer, clear.
We are not transmitting data here. I mean, yes and no. I mean, you can think about signals as data, but it's not directly translated, I guess. So the idea is the system becomes faster. Transient response is much faster because you can handle higher frequencies. Your system, you can push your system to work at higher frequencies. If you can push your system to work at higher frequencies, what is higher frequencies? It's just faster. Okay, this is what higher frequency means. Instead of that kind of slow oscillation, you get that kind of oscillation. So your system can move faster if it is a mechanical system, right? It can respond faster if it is electrical system of some kind. Just faster, okay? So settling time is shorter, typically with higher bandwidth, but more noisy, and this is big disadvantage. So here you can handle that. And the textbook claims that this is not as intuitive as root locus design, and I tend to disagree. I believe that after like 5-10 years of experience in frequency domain, it will become more intuitive to use than root locus methods. But definitely some sort of experience is needed here. Okay, so it's almost assumed for that type of methods. All right, so just to remind you a few things, basic things. What is DC gain of your system? Can you see that on that plot? DC gain of the system. Who thinks that we have DC gain of the system? Raise your hand.
Is it not just the GM and the IM?
No. Good try. Any other ideas what DC gain might mean? Yes.
It would be G of M of angle phi of M.
This is zero.
on the phase plot.
This point? No, this
Right,
is not
GM.
gain, this is phase. This is phase plot, this is gain plot, part of it, obviously, not the entire plot. So you do not have DC gain on that plot specifically, but what it means. What is DC? Direct current. That's from electrical engineering, direct current gain. It's gain when your input is flat, which is constant. Okay, so what frequency constant has? 0. So it's gain at frequency 0. So it's G, this is your transfer function of 0. Okay, this is DC gain. And this is what happens, minus infinity when you go to 0 frequency, right? Obviously, I'm not drawing it because I cannot draw negative infinity frequency. So this is where the gain starts. This is DC gain, okay? So what is gain margin of the plot?
GM.
This is that part, which means where this function of phase crossing the 180 or minus 180 or 540, negative 540, all the multiples of 360K starting from 180, okay, plus minus. So all of these lines, you will have crossing of these lines, how much gain below 0 dB you have. This is gain margin. Let's assume you have multiple points like that, then what gain margin is? Let's say it's crossing multiple times, going up, down, depends on number of poles here and there. What would you take as gain margin of that system?
The average of all of the.
No, not average.
Add all of it up.
It'll be the same.
You're taking worst case, worst gain margin out of all of them. And sometimes it might be even positive here, which is worst case, which means the system will be unstable. So you don't have any gain margin really. There's negative gain margin, if you wish, okay? MATLAB will tell you negative gain margin, but it's not really gain margin. You don't have any, okay? So you're taking worst case out of all of the crossings of 180, plus minus, all right? Same thing with phase margin. So phase margin is where your plot here crossing 0 dB, which means gain of, like, what is real gain? What is 0 dB? What is the gain of the system? Not gain 0 dB. So what is, by what you multiplying the input? It's 0 dB. What is 0 dB in regular units?
1.
It's 1. It's gain of 1. Because log of 1 is 0, 20 times 0 is 0, 0 dB. Okay? So you have system with gain 1, which means all the input gets to your output. And this is that point. So you have phase margin, which is above the 180, negative 180, depends on where you are at that point. If you want real phase margin, when you have multiple crossing points of gain, and gain will go up and down, again, you are picking the worst case, where the phase margin is the minimal. This is the overall phase margin of the system. All right? And bandwidth is very interesting thing. I told you already what that is. So you're measuring that from the flat part to the first minus 3 dB point. But it's interesting that in the textbook, they do not explain what happens if you start like that. Okay, what do you do with that? If you don't have any flat part, if you have, for example, 0 at 0, okay, what do? You get like that, and you have all kinds of things like that. What is bandwidth? Yes.
Between your phase margin and your gain.
No, not really. Would be, but doesn't have to be. So it's interesting that it's defined completely differently in different places. So be careful with like what you actually define as bandwidth, because for many systems it's not even defined. Yes.
It'd be between every part where you cross zeros, or like so. I don't know how to explain.
Yes, so typically what people do, they have some sort of proxy for bandwidth, like how wide that looks like after it falls. So they look from the right side to the left side, and they go like, oh, when I'm getting to the peak here, like I'm taking 3 dB from the peak, and this is where that band is. Okay, so going kind of backwards instead of going that direction and lowering by 3 dB. So it's like 3 dB from the peak, and you have other definitions for that as well. There is no unique definition for that type of systems. Okay, so be careful even to define what it means. Again, because textbook defines it very vaguely. Says from flat, but sometimes you don't have flat part. Z1. Okay, so do you know how to convert from dB to regular gain and from gain to regular dB? We started to talk about that a little bit. So number one, 20 log gain is gain in dB, but how you get back? How do you get back?
By 20,
It's 10 to the power of that gain in dB divided by 20. Okay, this is how you solve it backwards. Same equation, okay? How about radians to degrees? We will need it, both of them, for that lecture. How do you convert radians to degrees and back? Multiplying by 180 dividing by pi, or the other way around. Okay, depends in which direction you go. Clear on that? All right. So let's see first intuition. We will start with very simple controller, just gain, okay, preamplifier. You have some sort of K that you need to design, and you want to design it to get particular result. And this result will somehow relate to overshoot and other things. But we will connect it to phase margin. So you want to design particular phase margin to your system using only gain. So what gain does to your Bode diagram? Like if you multiply by some constant, what will happen to Bode diagram? Gain, which is the upper plot, will move up or down. Depends if K is larger than 1 or lower than between 0 and 1. Okay, so between 0 and 1 is like negative dB, and above 1 it's positive dB. Okay, so if it is positive dB, it will go up. If it is negative dB, it will go down. So scaling down your gain between 0 and 1. All right. So this is overall idea. Let's say you want particular phase margin to your system, and this phase margin is given by these points. Okay, this point C. This is where you want your phase margin. Now, obviously, your gain at that same frequency is not crossing 0, so it's not phase margin, right? What should we do to make it phase margin now? We need to take that gain and to pull it up, that the point B will be at point A. That's it. So we need to find like by how much we need to pull that up, that this will become our frequency of phase margin. This is the overall idea. This is the intuition behind it, okay? So if you want to achieve particular phase margin, all you need to do, you need to find on the Bode phase plot where you satisfy that phase margin, which is like where that phase is the exact number you want, okay? And then pull gain up or down to cross the axis exactly at that particular frequency, all right? This is a design procedure, okay, to achieve that phase margin. So here's how you do that. First of all, you have the transfer function g of s, then you have percent overshoot that you want to achieve. And hopefully you've seen some formulas which are connecting overshoot to zeta, which is damping coefficient. And then you have also phase margin, which is connected to zeta, computed, it is for second order approximation, is dominant poles. Okay, so you have all of these formulas which are connecting through zeta, overshoot, the phase margin. All right, and this is what we'll be using in that design. So what you do, you join Bode diagram of your G, just to see phase and gain. And then you have that formula to compute zeta from the overshoot, percent overshoot. Okay. Hopefully you saw some formula like that before. Okay, you put in computing zeta. From zeta you can compute phase margin, desired phase margin, like how much you want it to be, okay, to give you that overshoot. Again, this is based on second order approximation, so this is not precise. And this is why I'm saying, even when you use these formulas, eventually you will need to do simulation and to make sure that you get whatever you need. And sometimes you need also to modify a little bit, to fine tune it, to make it work, because this is all based on approximations, second order, which is not always the case in your system, right? Not always you have second order systems, all right? So you're computing that phase margin based on the zeta. So you have now zeta, phase margin, desired phase margin. And then you go back to your Bode diagram and you're looking where that kind of phase you have on the Bode diagram, which will satisfy desired phase margin minus 180. So why that formula? So just look at that thing. You want phase margin to be here, right? So this is z point minus z point. So this is angle of G minus 180, which is plus 180. This will be phase margin. This is exactly the formula. Well, G, angle of G plus 180 equals phase margin. Okay, just written in a different way. I just moved it from one side of the equation to another side. All right, so far, this is where this formula is coming from. And I'm looking what is that frequency, omega, at which my phase will be that numbers that I want. And there I will want my gain to be exactly 1 or 0 dB, okay, at that particular omega. So this is the idea. This is the intuition behind the design. So how do you compute that? Here you go. You have formula for that. It's just 1 divided by the gain at that particular point. Why is that? Because if you're using that gain K, it's 1 divided by G, absolute value, and multiplying it by gain, which is that G at that point, you will get 1, which is 0 dB. Like what would be that thing in dB if you want, this is without dB, right? This K computation is not in dB, it's like regular gain. What it will be in dB, that will be 20 log of that thing. Pay attention that log of 1 divided by x is minus log of x, which means it will be minus value of the Bode diagram at that point, okay? That's it. So your gain will be practically inverse of your value of gain at that particular frequency in dB, or 1 divided by K, which is 1 divided by gain, which is the same thing. Any questions on the procedure before we get to the example? Okay, so let's see one example. In this example, we have transfer function with integrator in the loop, which is making it a little bit more interesting. And we have third order open loop system, GS. We want to achieve overshoot of 9.5%. This is the requirements that you have. And we start with plotting Bode diagram of that system. And then you will have that kind of Bode diagram. Here you have some MATLAB code to plot that thing. Pay attention, I don't know how you define transfer functions before. Textbook defines it using the ZPK function. I don't like that function for whatever reasons. I prefer just to define S first as transfer function. I'm using TF function, transfer function. And that's how you define it. S equals TF of S. Quotes. And then you can use S as algebraic variable. And you can write any kind of transfer functions just using S by multiplying different things, dividing different things with S. And it will be just doing any kind of regular transfer functions, either in expanded state or factored state, whatever you prefer, like whatever is given to you. Yes, you can just define the G as 100 divided by S, divided by S plus 36, divided by 100 plus S, okay? Now I'm plotting Bode of that thing, not using default points, because I might not have enough points. It's sparse, too sparse between the points, and I want more precise numbers, potentially, all right? So I'm giving like 100,000 points from 10 to the negative 2 to 10 to 2. So you'll have from 0, 0, 1 to frequency, which is 100. Okay. And this is where I will have my gain margin, phase margin. Should I use these particular numbers? You don't have to. You can broader numbers, you can do it from -5 to 5 if you want to. It doesn't matter. Okay. It's just to fit what textbook is doing, okay? To fit the plots that you have in the textbook. They did it from -2 to 2 powers of 10, which is fine, okay? You get all of the information you need from that zoom to that plot, all right? You have these two things, and pay attention what you have gain as gain margin and phase margin. So you have gain margin of 73.8 dB. It's huge. And phase margin almost 90 degrees. It's huge. You don't have any overshoot. Okay, forget it. It's much better than you wanted in the first place. And closed loop system is stable. So you see, it even shows you the closed loop system stable. Yes. Done with the design, like I've got better overshoots than they wanted without doing anything with K equals to 1. Why would I need to do any design here? Any idea like why I should give some overshoot to the system if I don't have any already and it's stable and converges to 1, it's perfect step response. Why would I care to keep the design going
The behavior changes when you the closed loop.
What happens to behavior? So yes, but what happens? What's wrong with my design? Not my design, but no design.
Maybe you don't want the system to settle that quickly, like you actually want it to take some time.
Correct, but opposite from what you said.
Oh, okay.
So what happens is with that system will be extremely slow. Your settling time will be horrible. Yes, your overshoot will be zero. It will slowly, exponentially go forever. It will work like probably like elevators in our previous building. Remember what that was in the EC building? So this was that kind of design, I guess. Yes.
So I have a question, and this, you do not have to answer this, but so the 1/S+36 for like the motor and load, how is that equation, or how is that actually found? Like if you have a physical system, how do you make these equations from this physical system?
Okay, so you have multiple ways to do that. So first of all, you can do that from physical laws about like how currents work, Kirchhoff law,
Yeah.
and there is full development in that same textbook. If you go some chapters, how they develop specific things. But in practice, you typically do not know physics of the system, so you can estimate the parameters of the system. So you assume something on first order or second order, typically, because this is the easiest one. And then you send, for example, step response to each subpart of the system and seeing how it responds. So based on the settling time and overshoot, you can identify, for example, two parameters. All right. And then you're doing different kind of frequencies, you can identify Bode of that. Based on the Bode or step response, you can identify some parameters of the system. Okay. And those parameters you'll just put here as your transfer function.
Yeah.
Okay, because you know that there is relation, for example, between settling time and zeta omega, right? It's like sigma multiplication of zeta omega, right? It's minus 3.9 divided by sigma. Okay, this is approximately for second order, at least this approximation for the first order, second order, approximation for the settling time. Okay, so from that you can compute zeta and omega. So omega will give you, omega squared will give you free coefficient in your second order approximation, and twice zeta omega will give you the second coefficient in the polynomial of poles, right? So this way you estimate the system based on the step response, for example. But you have other ways to estimate systems. Okay, you have optimization, you have all kinds of tools to estimate systems, like full code. System
Like the
optimization.
term is, it's called system identification, like
Yes,
you
it's
could, like
like
a
you can-
whole field of. what
Entire
goes
field
on.
on,
So that's a
identify.
where you could have.
Yeah.
yes.
Actually, Ari, before you move forward, I did not fully explain, like, where does the minus 180 phase come from? Can you explain the theory behind, like, why is that particular phase the phase that you look at for like phase marking?
Okay, so this is coming from Nyquist theorem. Okay, all you're looking in Nyquist theorem is encirclements of -1 point, right? So what is -1? -1, what gain you have to that point? It's 1, okay, which is 0 dB practically in Bode diagram. And what is phase that you're handling here? 180 degrees and all the multiples of that negative axis. Okay, every time you cross in that point, this is 180 degree crossing in Bode diagrams. Okay, when gain crosses 0, this is exactly that point that you're encircling. Okay, so this is how far away your Nyquist plot when you rotate it. This is phase margin. Okay, or how far away you can scale that Nyquist plot to cross the margin of stability. Okay, so phase margin means how much you can rotate Nyquist plot until you lose stability, and gain margin means how much you can scale, inflate Nyquist plot until you lose stability. All right, so these are where these numbers are coming from, and you will lose stability exactly when your Nyquist plot is crossing -1 point, right, on the real axis. This is exactly the boundary condition where here it's stable, crossing that point, it's unstable because number of encirclements will change at that point. So this is exactly that point where you measure gain margin and phase margin. All right? Okay. So let's see what happens after that. And this is a response, step response and closed loop for our original design with k equals to 1, and settling time is 141 seconds. Okay, horrible. No overshoot, looks great, converges to 1 eventually, takes forever, right? So here are the computations. I'm going step by step, all the steps that I previously defined. Totally computing zeta, putting overshoot percent, which was 9.5. So putting that number here, computing that formula, get 0.6 for zeta. Then you put in that zeta in the formula of arctangent to get desired phase margin, and you get 59 degrees approximately, your desired phase margin, which is 1 radian. Now I'm computing angle where it's supposed to happen. So I'm looking for that angle, which will give me negative 120 degrees. Okay, so let's go back to our Bode plot. So what I'm doing, practically looking back at the Bode plot, and I'm tracing that line of the phase until I get to the point of negative 120.8 approximately. Okay, and this is why you need more points. This is why I plotted like many points, that you will not skip too many points. So you'll hit more or less that number somehow. Okay, on the Bode diagram, it's approximately, okay, still not exactly. And the frequency at which I get it is 14.82, 83. Okay, I'm rounding it down to 82 because my 180 is a little bit lower than it needed to be. So this is the thing that you're looking for. Okay, this is a number. Okay, so you found at which frequency I want my gain to be 0 dB. Okay. Now I compute what the gain should be, which is 1 divided by absolute value of the G at that particular frequency. All right, which will be, this is S plus 36, and this is S plus 100. So I'm replacing S with J omega. From omega I now know it's 14 radian per second. Okay, put in these numbers, use calculator, metal, whatever you want. You get that number. You put in all of these numbers here, computing absolute values of complex numbers, and then you get that gain. This is the answer for your design. Okay, 583. Now, what is that value? Can you guess what that thing is? What that point on gain diagram is? Even what I just calculated here. Like, you don't really need to go through that calculation. You can find it directly from the plot. What that value is.
How much gain you need to get to 0?
Yes, this is how much gain you need to get to 0, but what direction?
Up.
Direction up. What does it mean to have direction up? It should be adding positive gain, right, in dB. Since this is right now, it's something negative, right? So if you're looking on the plot, it's negative something. So do you know what that negative number is? Can you tell me how to calculate that negative number from what you see on the screen already?
But just be negative 583.
This is pure gains, it's not in dB. So you need to compute that in dB. It will be some number, whatever this number is, 20 log 583. Okay, you'll get some number, and you're taking minus that number. This will be that value on the Bode diagram. So what you'll get is negative 55.32 dB, this point here. Okay, if you're taking negative 55.32, adding to that 55.32, you get 0. Okay, this is what you want, to have 0. All right, so this is just inverse, it's like negative. What's that value in dB? That's it. Any questions? Yes.
A question on just negative magnitude in general. Is there any point where numbers become so far down that it becomes negligible, or are these, do we care about negative magnitude just as much as positive magnitude?
Yes, the magnitudes can become super, practically 0. Okay, 0.0000, whatever, where you can ignore them. Why would you care to ignore them? This is the question, because you have the entire plot, You have all of the values. Why would you care if it is
Why not
like
use-
zero, or why would you want to approximate it as zero? This is the question that pops up in my head. Yeah, sure. Some of them you can ignore. Why would you ignore them if you have the entire plot? It will not affect anything. All right. Any other questions?
Margin here is 55, 32.
No, the margin is the thing which you want here, okay? The margin is what we computed. The phase margin was 59 degrees. This is the margin. And the gain that we computed is 583.26. 14 dB is the same thing as 55 dB, right? This is the design gain, all right?
So how does gain margin play into this?
So you are not moving that point where it was 59 degrees gain margin, okay? You're just moving gain up or down in such a way that it will cross zero, and then this point will become your phase margin. This is the idea. Yes,
So we randomly picked that spot and then we're finding the gain.
not randomly, we picked it where your phase margin is the desired phase margin. So you picked the point where your margin was desired phase margin. It was not phase margin in open loop, okay? But it was just phase which contributed exactly the number of the angles that you wanted. And then you modified the gain to match 0 point exactly at that crossing point.
Where did
We make it crossing point.
Where did we pick that? That it was gonna be the,
I'm sorry?
where did we pick that point?
So here's how you pick that point, okay? So you have that original Bode diagram, right? So you go on that Bode diagram and you computed how much you want, which was negative 120. Okay? So you are looking for such a frequency on the phase where you have that number equal to negative 120. Okay, so you're moving, you're kind of looking at the point and getting to the point where phase is exactly negative 120. This will give you the point of omega. Like from there, you know what omega is, and this will be 14.82. All right? So this is how you know.
So we got that by subtracting 180, right?
Yes.
So if we wanted any point, we would subtract any number.
No, you don't have, you always subtracting 180 because this is what phase margin defined by. It's distance from 180. You're subtracting 180 because phase margin is defined by distance from 180. You're always subtracting 180, actually negative 180. Yes. So it's this is exactly the distance that you're looking for. You are prescribing the distance to be whatever you want it to be. Okay, and you're looking where it fits your criteria, and then you're modifying gain to cross it exactly at that point. Okay, where you will get that phase margin practically. So this will become your gain margin. Sorry, phase margin. Okay. So this is the overall idea, and the step response that you will get here will get you there by probably settling time of quarter of a second compared to 140 something seconds. Okay, but you will have overshoot, and overshoot in that case is like 8.64%, something of that kind for that type of design with single K. All right, so it's much better response, so higher overshoot. You will have to revisit if this is okay. All right, any other questions on that exercise?
Weren't we designing for a percent overshoot of 9.5%? Like,
We were designing for 9.5, yes, and we've got 8.6, which is better in a sense, okay?
9.5 or less.
9.5 or close, okay? So again, it's not exact thing, so you will never get exact because it's not second order function, and you have all kind of approximations here to
so
do.
that's still close enough to meet that.
So this is close enough to, yes. So you don't want it to be higher than 9.5.
Yeah.
9.5 is your kind of higher boundary. So you want minimal settling time typically, minimal rise time or T-peak time, and you want minimal overshoot, and you want appropriate bandwidths, things of that kind. This is what typically you want from control systems. Right? Any other questions? Okay. So now we move to lag compensator. So lag compensator is also very interesting and not very intuitive thing. Okay. So the idea is that we want to have steady state error without affecting too much else other things. And intuition will have to be even more difficult here than with constant gain. Okay. Because here's how it looks like. So if you're looking on uncompensated system, let's say this is the gain of uncompensated system, okay? And this is phase of uncompensated systems. So phase goes down somehow, gain goes down somehow at particular points, okay? And what textbook shows here is not exactly the intuitive thing that we need. Okay, so what it shows here is that your controller starts with practically 0 dB gain. So it's not affecting the DC gain at all. And then it goes somehow down, okay, because this is how the controller will look like, okay, this compensator. That will start with 0, then it will go down, then it will stop somewhere. And if you remember what leg controller is, you have 1 pole and 1 0, some gain. Okay, this is how it looks like, right? So what happens is you have pole here, and then you have some 0 here, and then it gets back. So you're lowering practically higher frequencies, so you making it low pass filter in a sense, so you deprecating all of the higher frequencies and you're keeping all of the low frequencies as they are. Okay, this is what the thing is doing practically. But the intuition goes completely other way around. If you want particular steady state error, what do you need to do to your DC gain if you want to improve it somehow? You don't need to keep it constant. What should happen to DC gain to improve steady state error? Should be increased. You want more gain. Like if you have some KV, okay, and you want to improve response to the ramp, you just multiply that KV by some constant to make it stronger gain, all right? And then your KV will become higher. And this is good for your steady state error, because steady state error is 1 divided by KV. Okay, so higher the KV is, lower the steady state error is. This is what you want. So you want to increase gain, but increasing gain will cause all kind of other troubles, right? Because if you increase in gain, what will happen? You will move your phase margin as well. Obviously, because the entire gain will go up. So you will move it lower, so you'll get worse overshoot and other characteristic transient response, okay? So what lag controller is doing, it's not preserving the lower frequencies. Like in the design, we will preserve lower frequencies just to be able to pull the entire thing up, okay? So actually the initial part, which is gain of that lag controller, will go up, and we will try to preserve the later part where all of the phase margin happens, okay? This is intuition behind it, how it actually works, okay? So you'll try to pull up the lower frequencies without touching the higher frequencies, all right? This is the overall idea. And your overall design, what will happen is that when you add in the lag designer, okay, you're practically moving your omega, crossover omega, where you have the phase margin, in particular direction, okay? So this is controlled system gain, and this is the original one. So your crossing point was here, and now it moved here. So you're moving phase margin to the left, where the phase is typically higher, because phase looks like that, okay? Typical system. So if you move your omega to that side, your distance to 180 will be bigger, okay? From negative 180 to your Bode phase, okay? Because it looks like that. So this distance will grow. So this controller helps to grow that distance. This is the overall idea. Now we have procedure, and before procedure actually, this is how real one looks like. So this is plot of the lag controller. So the Bode diagram gain will go down like that, almost like inverse sigmoid type of function. And phase will have some sort of dip here. And you will change the phase. So the idea is that you don't want to change phase too much by the dip. So this dip should be somewhere outside of your work area. Okay, and this is where the art comes in, like where you put all of these numbers. Typically, you have all kind of thumb rules, how you choose different things for that controller, but we will discuss more or less technical parts of it. And later I will discuss a little bit of how you play with the things, all right? So pay attention that this thing is never zero, okay? So you will add phase, actually subtract phase everywhere from your plot, original Bode plot of your G system, okay? So you need to take it into account somehow. You will still modify it, but not by much. You can assume that farther away in the tails, okay, you're not changing that by much, probably like 5-10 degrees, something of that kind. And we will try to compensate on that as well. And I'm telling you all of the things just to show where the next points are coming from, okay? So here is a procedure. This is just fault zero diagram of that controller. Here is a procedure. Let's say you have transfer function G in open loop. You want to achieve some overshoot. You want to optimize settling time error, not settling time, steady state error. And you want to find that leg controller which is minimizing steady state and also giving you overshoot and all the other nice properties of the system. Questions that they have in the textbook also sometimes reformatting the question of how to optimize steady state error by how much you want it to be improved, like tenfold or something like that. You want to improve steady state but tenfold. This is typical question. So I will show you also how to get that. Typically, you just need to multiply transfer function by 10. This is a gain that you'll be using, like 10 times bigger gain instead of original gain. But practically, you can convert it from ESS as well. So step number one, you plot in Bode diagram now of K times G, all right? And this K is the value that you need to achieve your steady state errors that you want. Either it's like 10 times more than the original one or whatever it is, you will get K using the previous characteristics, okay, previous design that we just showed. So you get your K, it achieves some particular steady state. Now you know what you want. So you will multiply by that constant, your steady state, all right? Now you plot in diagram already of that open loop, including the previous controller, which is preamplifier, all right? This will be your entire open loop transfer function, K times G. All right, second step, very similar to what we did before. You are looking for phase, okay, phase margin. You're computing that using zeta, using overshoot. So same steps, you get into the same phi of M, okay? Subtracting 180, which will be giving you that desired G location, like where you want it to be. And from that, you're finding that omega C. Now this will not be phase margin anymore, okay? This will be just some omega, which I call omega C, okay? Omega of controller. It's omega peak, where that downward peak will be, okay? Not phase margin in that case, all right? So it's omega C, we'll call it omega C. Now I also want to add to that a little bit of margin here, which I will call epsilon. And this epsilon will be between 5 and 12 degrees. This is what typically recommended. I pick almost always 10 degrees. And this is to compensate on this non-zero phase parts which are far away from the peak, okay, where you have that thing going down and going up. It's not going up precisely to zero. It's still lagging forever, okay? This is not asymptotic, this is real. So you need a few degrees to bump it up a little bit, to put it close to zero, okay? This is why that epsilon is here. Okay, so I'm giving it a little bit more of the space to be modified, right? So I'm computed that value where I want to change my gain. And again, computing gain the same way. It's 1 divided by the G gain at that particular point, or in dB it's 20 log of that thing, or negative dB of kg. Pay attention to this now, it's not G, it's kg, including my perfect steady state kind of open loop gain. All right, so far. So this is a procedure how to compute A, that gain that I want for that particular point. And here is a formula which identifies where all of the values will be for my controller. So controller will look like that. It will be that DC gain A, okay? It's not DC gain in that case. Just gain A, amplification, times S plus omega C divided by 10, and Y divided by 10. Number 10 you can play with. It's 1 decade before omega, which means it needs to be far away to the left from my phase margin. Okay, I want it to be somewhere there. Okay, why? Because I don't want it to affect my phase margin. I picked my phase margin. I don't want that lag controller to affect anything in the later phase. All right, so I'm picking it like 10, like decay to the left. It could be more than 10, but don't pick it like too far away because it will be too lower frequencies. Okay, and then the pole will be at S plus omega C times A divided by 10. Okay, this is just how you find the breaking point, and what will happen is, so you have that particular point, which is the latest breaking point, after which it's flat. Okay, remember how asymptotically it looks like? It's flat, going 20 dB to decay down, then again flat. This is how all the diagram of that thing is supposed to look like, asymptotically at least. So you have that point. How do you define the point before that? Is by that formula, omega C times A divided by 10. This is a second breaking point. Okay, so you'll have pole here and zero there. Okay, and they are separated, obviously, by a particular distance. Okay, so this is how you choose pole and zero. Textbook explains it in a little bit more complicated way, but at the end of the day, you will get the same thing. Okay, they have probably like 5 more steps. Doesn't matter. You get to the same thing. I short-circuited them to just given formulas. Okay. Any questions on the development? Now we'll do exercise to show all of the steps and to see how it works. Okay, the question is, you're taking previous exercise, which was same problem, same 9.5% overshoot, same transfer function, but now you want to improve previous example and to have 10 times better steady state error, right? And since you have integrator in the loop, to step response, you don't have any steady state error, right? The steady state error is 0 also because you have integrator in the loop. So you can talk only about KV and not KP here. So you want to improve KP, but nothing to improve. It's perfect. Now you're improving KV 10 times. And this means that your gain need to grow 10 times. Why is that?
Because ESS is equal to K times.
Because this is just DC gain, so it's G of 0, okay? When you multiply that by S, because KV, if you remember, it's limit of S times G. So you cancel in the zeros at 0 and pole at 0, and you're taking the rest of the G function at 0. And this will be whatever the gain is divided by whatever the first pole is and whatever the second pole is. Okay, this is your DC gain. If you want to improve it 10 times, you just multiply that entire DC gain by same number, which is 10. In that case, you want 10-fold improvement. So your KV will be multiplied practically by the same number, right? So this is your original transfer function, and you plot. You have also like 59.2, if you remember from the previous exercise, the desired phase margins that we wanted for the particular overshoot of 9.5%, right? And now, first step, we are plotting Bode diagram of K times G. So our K now is 10 because we want to increase gain by 10 times, okay, to improve steady state error. So we're plotting that kind of gain. If you remember, our answer for the previous K design was 583.26. And the transfer function, original transfer function, was multiplied by 100. You remember the transfer function? Just to remind you what it was. You don't remember. So it was 100. Then we multiplied that by 583. So we got that number. And now we want to multiply that number also by 10. Okay, because of the steady state error. So we will get that number, okay, which is pretty big gain. Okay, so this is the Bode that we are plotting as our open loop initial step. Okay, so we plotted that thing, and we get particular numbers here for, and ignore these numbers for a while. Okay, you just get the Bode diagram. But next step, what we are doing, we are finding such omega C, which is an omega peak, omega max, whatever you call it. such that the 10G, which is that same angle of that thing at that particular omega, will be the start phase margin minus 180 plus that additional gain, additional phase of 10 degrees. Okay, just to correct for the imprecisions in our approximations here. Okay, and this value will be minus 110.8 degrees if you just put in numbers in. Okay, so we are going again on that plot and looking where is the negative 110, where we will have that phase margin. Right, so this phase margin will be at 9.83 approximately radian per second. Okay, you're just scanning that point until you get to that thing. You're identifying what omega corresponds to that thing. And the gain that you will have here is probably around 40, 32, I don't know. Let's see. So it will be negative that number, okay, in dB. 24. So negative here is 24. Okay. Okay. So it's 24 dB, which is that kind of gain. Okay. Now, this has to be also negative 24 because you want to go down with that plot to 0. You want crossing point to be at that particular point, omega. So what happens here, if this is 24 here, you need to pull it down, so you need to subtract 24 dB. All right. And this is what will be the gain here. So A will be negative 24 dB. Any questions on that? We identified already 1 out of 3 parameters of our lag controller. Finally, we just put all of the other numbers inside the formula, and we get A is that number, okay, which we just computed. Omega C is that number that we computed from Bode diagram, which is that number, okay. And this is divided by 10. So this will be 0.983 instead of 9.83. And this will be same thing, just multiplied by A. We need to multiply also by that constant. So we'll get something like that. There's something close to 1 times something which is close to 0.06. Will be close to 0.06. Okay. That's it. This is the design. Any questions on the design part? Yes.
So first you get like a C, and then you compute a value 24, and then so you know that down to the 0.
Yes.
A.
So you have like extra 24 dB in your gain. So you want to remove it, so you need to multiply by additional thing, which will pull it down.
And I wonder why there is a omega C over 10, where 10 is.
Yeah, so this is, you want it, it doesn't have to be exactly 10. It could be more than 10, a bit less than 10. The point is that you don't want to change your phase margin with your peak. So you don't want your controller to be in the region where you're modifying that thing. You want it to be to the left, at least 1 decade to the left. Okay, this is why you divide by 10. So your omega of your actual peak, which is location of your pole and 0 of the controller, will be far to the left. This is what you want. And with this number, you can play a little bit. So this is how you play with the design. So you modify, divided by 10, you can divide by 9 or by 12 or by some other numbers. Epsilon could be 5 degrees or 10 degrees or 12 degrees, or so you can play with these numbers until you get characteristics that you want. And your characteristics will be always that response. So you'll compute closed loop step response or ramp response or whatever you're looking for. Okay. And if it satisfies your requirements, for example, this is not satisfying your requirements, okay. The design, which is from textbook directly, okay. It's not satisfying the overshoot. It's 10.5% instead of 9.5%. It's close, okay, but not satisfying the requirement of 9.5, which means this is no-go design. You need to modify it a little bit. Okay, so you need to play with numbers until you get 9.5% instead of 10.5%, okay? And other values are close enough. For example, like peak value is 0.59, which are all pretty fast, okay? And steady state error will be also pretty good. So all of the other values are fine, but overshoot is not great, okay, not perfect. Sometimes you can say, well, it's just approximation, right? So who cares? It's like 1% difference in overshoot. It's not realistically even to worry about it, okay? So if your elevator goes 10% up or 9% up, you will not notice, okay? It's a difference, no difference in physical reality, okay? So sometimes it's fine to keep it as is. Okay, you just say, well, I haven't satisfied all the requirements, but it's still kind of okay. It's not horrible. It's not perfect, but not horrible. And this is how in reality stuff works, okay? You never get everything perfect the way you wanted it to be. You always need to compromise on things. Okay, and this is one of the possible compromises, 1% above the needed one. It's not really that significant. Okay, so you can live with that. Any questions on that?
So the 10 is come from the echelon.
I'm sorry?
So the 10 is the echelon you choose.
10 degrees, yes. But divided by 10, it comes from just decade before, like omega divided by 10 comes from being far to the left. So I want to put controller far to the left, not to affect all of the phase margin location. And 10 degrees is because it's a function of phase, okay? It's not ideal. It's not like going down like a triangle and then flat at zero. It's not at zero. It's never at zero, okay? For any omega, it will be below zero, right? So it will never be actually, it will be zero only at negative infinity. So you'll have some extra angle added by that leg. And you want to remove that extra angle, which we haven't accounted for before. So we are accounting for it. Now, how much you will need to remove, this is again a question of design. You need to play and see what works better. That's exactly what you do in design. All right? Any other questions?